Alrighty, so now we're on page 3 of the review, and it's going to be a little bit easier until we hit number 16. That's going to be quite a bit of work, but I'm just going to work right here using the graphs and some colored markers. Even though I'm out of coffee in my cup, it's empty, I decided I might as well just move on. Okay, so number 12. We've got the graph of f. What is it the graph of? It's the graph of f. And the first question is, where is f prime positive? Well, we know that f prime is positive whenever f is increasing. So f is increasing from -2 to 2. So f prime will be positive there. Okay? Where is the second derivative positive? The second derivative is positive, right, when f is concave up. So remember that we know concavity is going to change somewhere in between the maxes and the mins, the bumps. It doesn't matter which way, max, min, max, doesn't matter. Concavity is going to change somewhere in here. But what I do know is that the second derivative is positively valued whenever our function f is concave up. So we're concave up from about, what is that, -5 to about 0. You know, so even if you put, you know, -0.5 or +0.5 or something, I'd still give it to you because, you know, we're just kind of eyeballing it for right now. But I'm just going to say when x is equal to 0. Okay, that's where the graph is concave up. And then it says, what are the critical numbers of f? So it means critical points. The critical points are where the maxes and mins are. So we'd have one critical point right here, which is -2, -1. And the other critical, by the way, that means and in math. Logic, right? And then the other critical point would be at 2, 3, I think? 2, 3.5? I don't know. 1. This is the origin, right? So 1, 2, 3. I'm going to say from 2 to 3.5. That's it. Number 13. We have the graph of f prime now here. F prime, meaning the first derivative of some function. So, where is f increasing? F is going to be increasing where f prime is positive. So, f prime is positive from -4 all the way to -1. So, from -4 to -1. And f prime is positive from 3 to 4. And so that means that f is going to be increasing from 3 to 4. Where is f concave up? F is going to be concave up where the graph of the derivative is increasing, right? And the graph of the derivative is increasing in a couple of places. It's increasing over this little interval here. So it's concave up from -4 to -3. And it's also increasing from 1, so from 1 to 4. So 1. So when f prime is increasing, I know that the graph of f is concave up. If f of 1 is 0, is f of 0 positive or negative? Explain. Okay, so let me find another color. Let's do red. So I know that f of 1 is 0. So my function, the original function graph, passes through this thing. And I want to know, is f of 0, so f of 0, whatever it is it positively valued or negatively valued? Explain. Well, what I see here is that from -1 to, well, from -1 to 3 is that? -1 to 3, f prime is negatively valued. What that means is that my derivative, or my original function graph, has to be decreasing. So my function f is increasing from -4 to 1, and then it goes to decrease. So from -4 to 1 is decreasing. And it's decreasing, or sorry, it's increasing from here to right about here. And then it starts to go to decrease. So it's decreasing, 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 right? And then this thing goes, oops, I'm sorry, I made a mistake. Damn it. I didn't say that. I'm not going to edit this video and remove that because I don't know how to edit videos really. And so the derivative is less than 0 on the interval from 0 to 1, which means that f has to be decreasing. So what that means is if f is decreasing, so I'm okay here. If f is decreasing, then it's going to be positively valued from 0 to 1 at least. So it would be positive. I hope that makes sense. I'll try and think of saying it a better way, or maybe I'll redo it later, but what I showed and what I said is true. But maybe I just didn't do it well. Let me know by leaving a nice comment. And hit the thumbs up button too, and subscribe, and hit that bell. No, I'm kidding. Okay. Anyway, the graph of the function f from 0 to 10 is shown. Several points are labeled. A, list all labeled points for which the derivative is positive. So again, I'm looking at the graph of f. And I want to answer some questions maybe about the derivative or the second derivative. So, list all labeled points for which the derivative is positive. The derivative is going to be positive whenever f is increasing. So f is increasing here and here. So all of those points labeled on the graph are going to be included, right? So let's see. Part A, point B, the derivative is going to be, now A is an endpoint, right? So I'm not going to include A. So even though the function's increasing here at A, that's the point, well, maybe I should include A. I'm not sure if I should include it, but anyway, I'm going to include points here for which the derivative is positive. So it's increasing here, so that's going to be point B. And then over here, point F and G. So you notice I'm not including those endpoints of the interval because, you know, we're going from increase to decrease there, we're going from increase to decrease there, or decrease to increase there, and the endpoints are special. So it's really what you're looking for are the points in between those sort of little endpoints that make up those sub-intervals. Okay, so anyway, for the points for which the derivative would be positive, I would say it's B, F, and G. And I'm right, because I just looked at the key here. Okay, list all the critical points of f. The critical points of the function f are going to be the places where we have bumps, right? So, you know, those are places, remember, where the derivative will equal 0 or not exist. So guess what? At this point here, we're going to say the derivative doesn't exist because it's an endpoint. So it's going to be A, C, because the derivative would be 0 there, E, derivative 0, H, derivative 0, and then this other endpoint here, K, I think it is, the derivative doesn't exist there either. So those would be the places where the derivative does not exist or equals 0. That's what makes a critical point or forms a critical number if you're looking at the graph of the derivative. And in part C, they want you to list all the labeled points at which the second derivative is positive. Well, the second derivative is going to be positive where our graph is concave up. So, I don't know how this is going to work, a yellow marker, but this graph here is concave up, like in this region here. So the second derivative is going to be positive there. And, you know, between this bump and this potential inflection point here, what we have is, I would say D and, is that an E? D and E. Now, here's another thing. So I'm thinking as I'm looking at this, I'm sorry that I'm like hesitating. But the graph here is concave down and the concavity changes somewhere in between here. Maybe it changes around here, like around D. And it's more concave up from here to here. So it's kind of hard to tell. So I would say that E would be the only point for which the second derivative would be positively valid. And of course all these other points in between, but he just wants you to specify on these particular points that are labeled. That whole region of concave upness there, or concave downness, would mean, you know, derivative positive when it's smiling and negative, second derivative, and second derivative negative when it's frowning. So, but anyway, E is kind of caught in between like two inflection points, so we're safe to go with E. 15, I said to skip. You don't have to do any curve sketching, especially something like that. That's a nightmare. I mean, it's not a nightmare, but it's a pain. Now this one, this is going to take some work. Not for the first row. First row is easy, right? We have a position function, we have velocity, we have acceleration. And this function right here happens to be position. So if I want to evaluate position when x is 0, I just plug a 0 in and I get 0. And if I want to evaluate at 1, I plug a 1 in and I get 1 minus 2 is negative 1 minus 6 is negative 7. And if I plug a 2 in, I'm going to have 16 minus 8, which is 8, minus, wait a minute. If I plug a 2 in, I'm going to have 16 minus 8 minus 12 is going to be negative 4. Okie dokie. So this is my version of editing a video, which isn't very good. But what I realized when going through the video that I had posted for page 3 is that when I took when I was doing the derivative using the limit definition, I forgot to distribute over several terms, and so I didn't want it to be wrong in the video. So I'm going to redo that part. Okay, so I believe, let me just move my window here. I believe what I cut out of the video, and we're going to see, is that I filled this in. I filled this in here. Okay, so again, we have this position function, x of t. And if I want to evaluate it at 0, I can plug the 0 in and I get 0. If I evaluate it at 1, I get 1 minus 2, which is negative 1. Minus 6 is negative 7. And if I plug a 2 in, I'm going to have 16 minus 8, which is 8. Minus 12 is negative 4. That's the easy part. Where I made the error is going from position to velocity, because it's a long, nightmarish problem. Okay? And so this is what I'm going to do. The function, let me just, sorry about this, but I'm going to move my camera over here. Okay, the function is x of t is equal to t to the 4th minus 2t squared minus 6t. And here we go with the camera again. Come on. I hope my little Elmo isn't like conking out on me, because I've been using this thing for years and I really like it. Can we please? Can we, huh? Can we work here? Maybe we can work together, Elmo, you and I. Maybe? What do you think? I'm gonna turn on the light. Not the fancy light, but the room light, because it's off. That seems to help. Alright, sorry about that. There's always an issue, isn't there, when it comes to me? Okay, what I'm going to do is I'm going to rewrite this. I'm going to change the name to F and X. So that means I'm going to replace all the T's with X. So it's the same function. I just want it in this form to kind of help you, because I know some kids and notation don't go hand in hand. Okay, so if I want, so I'm telling you that my position function, I just changed the name of it. It's now f of x. Okay, so if I want to find velocity, I know that the derivative of position, which I'm now defining as f, or is equal to velocity. So since f is now my velocity function, because I said it was, the derivative of that is also going to give me velocity. Okay, so no difference here. But in order to find the derivative function, I have to use that limit definition as h approaches 0 of f of x plus h minus f of x all over h. And because this is a quartic or fourth degree polynomial, if you're not familiar with Pascal's triangle and binomial expansion, then this is going to become a nightmare real quick. Now, I am familiar with Pascal's triangle and binomial expansion, and I'm sorry if you hear noise in the background. My dog's ripping a paper plate to shreds. She's mad because I won't play with her yet. I've been playing with her in between videos, but she wants more playtime. So stop doing that, Ella. So even with Pascal's triangle, I forgot to distribute in the last video that I uploaded. And, you know, then when I started combining things, I didn't catch my error, I couldn't find my error, and so anyway, I rewatched that part of the video and decided, you know what, I need to redo this. Okay, so let's do a flashback for Pascal's triangle, because I am not going to plug x plus h into this thing and FOIL it twice and then combine and then FOIL the two trinomials. Not doing it. And neither should you. So remember, let me just write a few. Pascal's triangle, which you should know. It scares me that you don't, but hey, what do I know? Pascal's triangle starts with a 1 up on the top. Looks like a pyramid, right, or a triangle. And every term or every row starts with a 1 and ends with 1. So this is 1, and these two are 1s always, automatically, and I'll show you why in a second. Okay, to get the second row, I start with a 1, I do 1 plus 1 gives me 2, and then I end with a 1. For the third row, I start with a 1, I do 1 plus 2 is 3, 2 plus 1 is 3, and I end with a 1. And I keep doing that, so I start with a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and I end with a 1. And you can do that infinitely for the rows of Pascal's triangle. Now, I want you to know that this diagonal right here represents the row number from row number 1. And here's why. If you have a binomial, meaning two terms raised to a power, a plus b to the 0 is 1, right? So this right here is the 0th row. A plus b to the first power, well, it's just a plus b, or 1a plus 1b. So these numbers in each row going across, they represent the coefficients for each term in the binomial expansion. Okay, so I'm in row 1, which is this row, because that's the 1's in the diagonal. So it's this row here, 1a plus 1b. A plus b squared, well, so it's a square, so the row number corresponds with the power, or the degree. So I'm looking at row 2, and I'm going to have, so here's how you do it too, by the way. You start out with the first term in your binomial to the highest power, and then as you go along, it's going to decrease in power, and the second term, you start with b to the 0, and then it's going to increase in power. So you'll see that as we move along here, but this is going to be 1 times a squared, so a squared, plus 2 times a, b, so a to the first b. You see, went from 2 to 1, and here there was no b, this was b to the 0, now this is b to the 1, and then plus b squared. So a squared, a to the first, a to the 0, b to the 0, b to the 1, b squared. So the first term in the binomial is decreasing in power, while the second term is increasing in power, always. Okay, a cubic. I'm going to go to the third row of Pascal's triangle to get my coefficients. Right, Ella? So yeah. And we're going to have a cubed plus 3a squared b plus 3ab squared plus b cubed. Let's do one more, just because I'm having so much fun. A plus b to the 4th. Well, that's going to be, again, here's the 4th row. And the coefficient of the first term is always going to be 1, so it's going to be a to the 4th, right? Plus 4, a cubed b, plus 6a squared b squared, plus 4ab cubed, plus b to the 4th. Oops. So, this is much easier to expand something out than, plugging in an x plus h and trying to do it by foiling and combining and distributing and all that nonsense, okay? So, I need to figure out what is f of x plus h. Well, that means for every x in my formula, I'm going to put a parenthesis, or in my function, right? So remember, I changed the function to f of x to make it a little bit easier, so that way the x is in the h and f kind of matches with this formula. But I could have written, x of x plus h minus x of x using, so see, that's why I didn't want to use the x, that's why I didn't want to call it x anymore, because I thought it might confuse you. So, I'm just using what we're familiar with. Here's the function, and now I've got to put an x plus h everywhere I have a parenthesis. And I've got to expand this nightmare out. Alright, and it's really, really easy to make a mistake, especially when you know how to do it, because the more you know, the faster you go and you make mistakes. Also, at the time I had done this, I had been like 3 hours making videos at that point, so I was tired, and it doesn't matter. I'm redoing it, so hopefully I don't screw up this time. So I'm going to expand this out. This is a 4th degree polynomial using Pascal's triangle. Okay, so x plus h to the 4th is going to be x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. Right? So this nightmare right here is the expansion of that. I haven't even done those yet. Now, underneath, I'm going to expand this one. Okay, so I've got -2, and if I expand the square, I'm going to have x squared plus 2xh plus h squared. So this is the expansion of that term. And then finally, if I distribute the -6 here, I'm going to have -6x minus 6h. So this is after I've used the distributive property with the n. So now I'm going to put this thing together. Okay, so all this mess is x plus h to the fourth. So let me move way over here. It's x to the fourth. I'm going to put my limit notation there, right, because this is the first piece of the formula, right? So it's going to be x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. Ooh, now I didn't factor this in, so I'm going to distribute and include that right now, okay? So minus 2x squared minus 4xh minus 2h squared. So this here I'm distributing and entering it into the formula. Minus 6x minus 6h. All of this is my f of x plus h. Minus, this is part of the formula, f of x. Well, f of x is x to the fourth minus 2x squared minus 6x. Okay, so this is minus f of x over here. This is my f of x plus h over here. And if I go ahead, let's use lavender. If I distribute this negative sign now, this is going to become a positive, this is going to become negative, this is going to become positive, and this is going to become positive. Alright, so that way I didn't have to rewrite it. And now I can start canceling stuff. And the stuff I'm going to cancel is the x to the fourths. So those are going to cancel. Zoom out here a little bit. 2x squares are going to cancel, and the 6x's are going to cancel. So what I have then is the limit as h approaches 0 of 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth minus 6h, it looks like, all over h, and I hope I didn't leave anything out. I did leave something out. I left this 4xh out. So it's a minus, so let me include that in there in case I need it. And now I'm going to factor out my h. So the limit as h approaches 0 of h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed minus 6 minus 4x all over h. And the h's cancel. And at this point, I'm going to plug my 0 in and take my limit. And when I plug the 0 in, anything that contains an h is going to disappear, right? So this term is going to disappear, and this term is going to disappear. So what I'm left with is 4x cubed minus 4x minus 6. Now those of you who know the power rule, remember the original function was x to the fourth minus 2x squared minus 6x. So if we were to use the power rule and take that derivative, we'd have 4x cubed minus 4x minus 6. So guess what? A lot of work to get to this, but you can verify using your power rule. Those of you that don't know the power rule, you gotta make sure you don't make any mistakes here, and that's hard, especially with the quartic. So, what is this? This is my velocity function now. I took the derivative of position and I got velocity. Okay? And in fact, I can say that I can call this v of t is equal to 4t cubed minus 4t minus 6. Why am I doing that? The original function was x of t, which was t to the fourth minus 2t squared minus 6t. So the derivative of position gives me velocity. And you see I'm with the same variables and everything that I started with. Now guess what? I can use this function. Ella, really? I can use this function to fill in the table for velocity. There's the function, there it is. Okay? So this is the row for velocity. So, you know, if I plug a 0 in here, my velocity is -6. If I plug in a 1, I get 4 minus 6 is -6. If I plug in a 2, I get 32 minus 8 is 24. Is that right? 8 times 4 is, I'm sorry, 8 times 4 is 32, minus 8, let me use my calculator just so I don't screw up again, because that's just the kind of mood I'm in. So 8 times 4 is 32, minus 4 times 2 is 8, that's 24, minus 6 is 18. I don't think that's right. It could be. Let me look at the answer key. Yeah, alright, it's right. Okay, that was filled in. Well, now I have to do one for acceleration, right? I have to fill in what's in here. Well, bummer, because guess what? Now I have to take this and find its derivative. Using the power rule, I know that the derivative of velocity equals acceleration, and by power rule the acceleration is 12t squared minus 4. But you can't do it that way. So, let me rewrite this. Markers are bleeding through. So v of t is 4t cubed minus 4t minus 6. Now again, if you want to write it, you can call it, you know, I don't know, v of x if you want to. You can call it whatever you want. You can call it f of x again if you want, g of x. So if you like it in terms of x better, okay, just do that. Again, at the end you'll want to, you know, replace the x's with t's and go back into the function in terms of t, because that's what you started with. But now I have to take the derivative of this thing. Okay, so I need the limit as h approaches 0 of f of x plus h minus f of x all over h. And I got to figure out what is f of x plus h for this thing. Well, it's 4 times x plus h quantity cubed minus 4 times x plus h minus 6. And this one will be a little bit easier because it's a cube, so it's not going to be. Still, I'm going to use Pascal's triangle. I need the third row. So this is the third row, okay, because there's a 3 in the second position. So that's going to be equal to 4. Now I'm going to expand this out. X cubed, right, plus 3x squared h plus 3xh squared plus h cubed. See how easy that is? And I'm going to distribute here negative 4x minus 4h minus 6. And now I'm going to distribute this 4 in here. So we're going to have 4x cubed plus I'm doing it again. 12, ignore it, 4x cubed plus 12x squared h plus 12xh squared plus 4h cubed minus 4x minus 4h minus 6. That's just my f of x plus h. And of course, I know what f of x is, so we've got the limit of 4x cubed plus 12x squared h plus 12xh squared plus 4h cubed minus 4x minus 4h minus 6 minus, as part of my formula, right, that I'm using this minus, f of x. Well, f of x is 4x cubed minus 4x minus 6. So again, here's my f of x here. Here's my f of x plus h stuff all right there. Now I'm going to distribute this negative sign. So I'll use lavender. A negative times a positive makes this a negative, a positive, and a positive, right? So I'm just changing the signs. Again, I'm changing this to a plus. That way I can cancel stuff. And I can cancel the 4x cubes I can cancel 4x, and I can cancel the 6's. So the simplified version of this thing is the limit as h approaches 0. I'm going to factor out the h too, okay? Factoring out an h out of every term as I go. So I'm left with 12x squared plus 12xh plus 4h squared minus 4 all over h, and those are going to cancel. And now if I take my limit, that means I plug the 0 in, and any term containing an h is going to go bye-bye. So this term's going to go away, and this term's going to go away. And so what I'm left with is 12x squared minus 4. Okay, and you know, that's what we had gotten on the other page, bloop, 12t squared minus 4, when we took the derivative using the power rule. So anyway, this is my acceleration. And now that I have that function, I can answer the questions in acceleration column, or a row. There's acceleration. So if I plug a 0 in, my acceleration is negative 4. The acceleration at time equals to 1 is going to be 12 minus 4, which is 8. And if I plug a 2 in, I'm going to have 48 minus 4 is 40? No, 44. And that's it. So it was a nightmarish, hellacious problem. I don't know, I pictured George like laughing as he wrote that one up. You know, to do something like this when you know easier rules of derivatives, it's a piece of cake. But to do it this way on a quartic, it's a lot of work and it's really unnecessary. I can assure you that your test will not contain a quartic where you have to find, you know, 2 or 3 derivatives by hand. Okay? So anyway, it's good practice for you using that limit definition, but it's a little bit over the top. Alright, so I hope that helps. I hope you have a great rest of your weekend, and I'll see you next week.